wrong. I like. Well, I would say like swiping. I really like it.
Hi. Nice to see you this morning. I'm sure you're all glad to be back here for this fine weather we're having today. We'll have we'll wait just another minute or two. I think it looks like, you know what, this is probably all that's going to be here today. I have a feeling we're at about 30%, which is really great, all things considered. So why don't we get started? I have a few announcements to make, and then we'll get started with today's content. I mean, I don't want to be here any more than you do. I don't mean here with you in this classroom. I mean here in London this time of year. So I feel your pain, as it were. I don't mean to say that I wouldn't want to be here teaching this class. You know what I'm saying. Sorry. Okay, so let's get started. I want to talk a little bit about the final exam that's coming up, a little bit about the midterm exam, and then let me hide floating meeting controls. There we go. Okay, so you probably all know where the final exam is going to be. The schedules have been announced. For whatever reason, we were split up well across campus for a while. Initially, we were going to be some of us in the education gym, and then another small group of like 20 people here in arts and humanities, which is like a mile away. Somewhere along the line, they realized that was a big stretch. So they put all of us into 2 rooms in North Campus building, which is a lot better from my perspective, because then I can sort of see both rooms. So they're, as far as I can tell, those 2 rooms are right next to each other. You'll know where you need to be when you log into your exam schedule, but basically it's it's alphabetical, right? So first half of the alphabet's going to be in the larger room, second half of the alphabet's going to be in the smaller room. This is Tuesday, April 21st. Not the best day, but not the worst. So it's sort of midway through, a little bit the beginning of the second half of the exam period. So it's not bad, and it's in the afternoon. Again, it could be much worse. We'll have lots of time to prepare for it towards the end of this regular term, as the month goes on, towards the end of March and the beginning of April. I'll have lots more to say about the final exam. But for now, keep in mind that the final exam is, let's go back here, non-cumulative. In other words, it covers only the second half of the class. So we're here, we just finished our reading week, and we're going to talk about inference and induction. We're going to talk about reasoning for the next 3 weeks, really. We're going to talk about thinking and reasoning this week, next week, and the following week. Then we'll talk about decision-making, problem-solving, and expertise. I've broken up the lecture on problem solving into 2. It's 1 chapter, but there's only a little bit of content in the chapter on creativity. So I added a lot of my own additional information to that lecture. So we'll have 1 separate lecture on problem solving, 1 separate lecture on creativity, expertise, and then we'll have the final exam on that April 21st. Same format. I'm likely going to and this is what I did last year as well, the relative balance of multiple choice to long, short answer type questions shifts a little bit in the final exam. There will be relatively more multiple choice questions on the final exam. It's about 2/3. There's a couple of reasons for that. One, it makes it a lot faster to get it marked. And so I've built in more multiple choice questions for the final exam. So there'll be a higher proportion. If you really like the written questions, there'll still be some, but it won't be as many. That lets me get things marked and get your grades in a lot faster than it would be otherwise. I've contemplated moving to all multiple choice, and I probably will eventually for this class if it's a 300-person class. But I also kind of like the written questions. Some of them are enjoyable. So I probably won't give them all up. But that's what you can expect for the final exam. But it'll essentially be a similar format. It'll be mixed, and it'll cover things in roughly the same way. We have a quiz next week. Quiz next week covers the lecture from today and the content for next week's class. We've got 3 more quizzes. We've got quiz 3, 4, and 5. Remember that I only take the top 5. So if you've missed a quiz or if you miss a few questions on one of the quiz and it isn't a perfect score, that's the one that gets dropped, and I take the 4 highest. Any questions on that before we get? Midterm results are coming soon. The TAs should be finished with the marking probably today, tomorrow at the latest. I'll then review everything once more. My goal is to have if you've taken the midterm 2 weeks ago, my goal is to have your marks available by the end of this week on Brightspace. For those of you that have approval to take a makeup exam, I'll send email to you later today to let you know where and when. But I think most of you already know that the makeup exam is this Friday at 9:30 in the morning in 1120 WIRB building. So that if you're taking a makeup exam and you're writing it with the regular class and not with accommodations, I'll be sending something to you today, and you'll find out it's the same exam. There's nothing different. It's just the same exam 2 weeks later. And you'll have the same amount of time to write it. Any questions on the midterm? Okay, so before we get started with today's content, how about the good news? Who's got something exciting to share? Either a good news story, something exciting or fun or funny or comical that happened over the February break period. Yeah.
OSAP cuts.
Sorry?
Like Doug Ford's like OSAP cuts.
So yeah, is that good? That's good news?
Not good news.
That's not good news. No, so the question was the Ford government shifts in how OSAP works. Apparently this is an issue for many people, and what I understand is that it shifts the balance to loans more so than grants, which is a little frustrating because you'd like to be able to afford to go to university without having to borrow the money if you're dependent on OSAP. So not good news, but certainly a discussion point worth having. There is a little bit of good news tucked in there, by the way, and that is that, and this is sort of hidden, I think, a little bit from some of the interest in how the way OSAP is changing and the fact that tuition will go up next year as well, is that, tuition hasn't gone up since 2017. So it's been a long time, but at the same time, the provincial grant, which is how the province funds university for operating expenses, irrespective of what you pay for tuition, also hasn't changed since 2017. And one of the reasons that your classes have gotten larger and larger is that Western has been essentially running on the same amount of money they had in 2017, now in 2016. So that will also change. The government is providing more money in the form of grants and funding for universities. So that's the good news. The bad news is shifting OSAP to be more loan dependent. So it's never all good news. So there's some good with that, but as a student, I wouldn't be very happy about the shifts in OSAP or tuition changes either. So that was a very guarded bit of good news there, Cameron.
Right.
That was bad news. So let's shift over to some good news. You had something. Your dog's 6th birthday. Happy birthday to your dog. What's your dog's name? Parker. Happy birthday, Parker. Lovely to have celebrate Parker's birthday. So is this Aquarius? Is it Parker and Aquarius?
I think so.
Or is it the next Aries? All right. I care about astrology, as I'm sure you know. Good news.
Valentine's Day, I was at this club and I was like setting strangers up with each other, and one pairing was successful, and I felt like a fairy godmother.
Well, good for you, pairing up strangers at a club on Valentine's Day. That sounds like a really exciting way to spend the break, and it was successful.
Yeah, they were talking for like half an hour. I didn't see them after that, so I was
Okay, so from your perspective, it was successful. The last time you saw them, success. If anything happened after that, it's out of your control. So good news. Any other good news or exciting stories? Anything funny happen over the break that anybody wants to share? Interesting tales. You're just all really pleased to be back on campus, I can tell. Okay, we'll keep it up. If anything arises, feel free to interrupt and share some exciting good news, because I'm sure we can all use it. Okay, we're going to talk about reasoning and logic for the next 3 weeks, but in different ways. So first 10, 15 minutes of today's lecture is going to be sort of setting up the kinds of reasoning and thinking that we're going to talk about. But what you should keep in mind is that reasoning is what most of us would describe as thinking. This is sort of an active thinking process where you're trying to do something. You're using your cognitive abilities. You're using memory, similarity, concepts, and executive control to do something. So this isn't just, I remembered something. This is, I really want to solve a problem. I really want to do something. I want to predict something. So going beyond the given information that you're confronted with in order to comprehend a situation, which might mean making inferences or deductions. So making some predictions about what you might see or expect. Taking knowledge about what is known and drawing conclusions, and essentially discovering new things by thinking about it. So this is using what you have in terms of System 1 and System 2, your language ability, your memory ability, all of the things we've been talking about for the last few weeks, using that to accomplish the goal of solving a problem, discovering something new, comprehending something in a different way by using your mental power and cognitive abilities. So here's a taxonomy of different kinds of reasoning. We're going to talk a lot about deductive, inductive, and causal reasoning, but we'll talk about some of these others a little bit. So I got 2 slides sort of detailing, 2 or 3 slides detailing the kinds of reasoning. We'll talk a lot about some and just a little bit about some of the others. Deductive reasoning, which is next week's lecture, is logical necessity. This is where you have some premises and they lead to a conclusion that if the premises are true, the logical deduction is also true. And so we'll talk a lot about that next week, how humans do that, and often how they fail to do that, because logical reasoning, deductive logic, can be really cognitively demanding. It's not an easy thing to do. It doesn't come naturally to most of us. What does come naturally to most of us is inductive and abductive reasoning. So we're going to talk today about inductive reasoning. That's where you generalize from observations. You look around, you observe, you remember things, and then you try to draw conclusions from that. These conclusions might not be guaranteed, and that's where a lot of the heuristics and biases come in. So an inductive inference or an inductive generalization is one that is probably true, but not always. And that's where deductive reasoning differs from inductive reasoning. You got true premises you can trust, you can make valid deductions, and you can guarantee that the conclusion is also going to be true. But induction, you just kind of hope that it's true. Just like if you set somebody up at a club on Valentine's Day and you observe that they're having a good time, you might make an induction that, well, they're still having a good time because as far as you know, the last time you saw them, they were doing fine, right? And you don't have any additional information. Abductive reasoning is where you may have several possible explanations or possible deductions, and you try to arrive at the one that's probably the most likely. So in addition, it goes a little bit beyond inductive reasoning by saying that, well, there are many probable causes, many probable explanations, and this one seems the most likely. So you're trying to find out which of those probable deductions is the most likely explanation or the most likely prediction. We did already talk a little bit about analogical reasoning, and we're going to talk more about reasoning by analogy when we talk about problem solving in a few weeks. Analogical reasoning is when you know something, you know how a structure works, you know how a system works, and you use that analogy to solve something else. We talked a little bit about analogy when we talked about Kempton's study on metaphors for how your thermostat works. So by analogy, if you think a thermostat is a switch, you might reason about other things, the way your thermostat works, as if it were similar to other switches that you know. It either turns on or it turns off. So that's an example of reasoning by analogy. We're going to talk about causal reasoning next week when we discuss deductive logic, but this is a specific subset of these kinds of reasoning where you're trying to determine the cause. Talk a little bit about it today, talk a little bit about it next week, but you're trying to figure out what made something happen. In other words, if you If you were to set somebody up at a club on Valentine's Day and they did not get along, you might, well, why didn't it work? Was it something I said? Did I pick the wrong two people to set up? Did the wrong song come on just as I was trying to set them up? What caused this negative interaction? And so you often think backwards a little bit of retrospective analysis to try to figure out, well, what caused this to happen? So causal reasoning is also dependent on noticing correlations. And we'll talk a little bit about the relationship between correlational reasoning and causal reasoning today. We're going to talk about probabilistic reasoning when we talk about decision making, because decision making often involves assessing probabilities. So does that make sense so far? So we've got 6 different kinds of reasoning, and we've given some examples here. So for deductive reasoning, all humans are mortal. Dr. Minda, that's me, is a human, so therefore I'm mortal. If those first 2 premises are known to be true, the conclusion is also true. We think this way all the time. Even though we don't always get it right from a logical deductive standpoint, we often make conclusions about things based on what we understand. When these conclusions are incorrect, it usually shows something like a representativeness heuristic, where you think that if a person is a member of a category, they have all of the attributes of that category. And that would be an example of this kind of deductive logic framework not giving you the correct answer. Inductive reasoning is bottom up, so every swan I've seen is white, therefore all swans must be white. So you make observations and you try to draw a generalization from that. Abductive reasoning, we choose the simplest and best explanation. The floor is wet, it probably rained. Lots of other possibilities, and I'll talk a little bit about that today when I talk about hypothesis testing. But you try to find out what's the most likely and simplest explanation. Analogy, things like an atom is like a tiny solar system. That would be reasoning by analogy. Causal reasoning, smoking causes lung cancer, therefore quitting smoking reduces the risk. And probabilistic reasoning, which we're going to talk about next week, which is often framed as a Bayesian type of analysis, where you understand the differences between the probability of a particular disease and maybe compare that with test results and take into account the base rates of occurrence. Other kinds of reasoning, which we're going to talk a little bit less about, but you should probably keep in mind because many of these affect the kinds of reasoning that we're going to talk about in class today. Counterfactual reasoning. This is something that we imagine when we're thinking through or solving a problem. Counterfactual reasoning is trying to consider what would happen if something did happen, even when it didn't. Imagining what if alternatives to past events. This can be key in things like trying to determine cause. So, as I mentioned, when you're thinking about determining the cause, you often look backward. If you're trying to test hypotheses to determine cause, you often look backward. You might, sorry, I keep using the example of setting people up at a club on Valentine's Day, but it actually works really well in this case. Suppose you had set somebody up and it didn't work. And then you think, well, what if I had set them up with this person over here? Maybe that would have been the better match. That's an example of counterfactual reasoning. You did not set them up with this other person, but if you had, would it have worked better? Would some other outcome have happened? So that's an example of counterfactual reasoning. You're thinking about things that did not happen, but trying to figure out what might have happened if it had worked out that way.
So would the gambler's fallacy be under that reasoning?
So gambler's fallacy comes more into probabilistic reasoning, where you assume, and we'll talk about the gambler's fallacy in about 2 weeks when we actually 3 weeks when we talk about decision making. A gambler's fallacy has at least 2 origins. One is an understanding of what randomness looks like, and the other is sort of an understanding of whether or not something should be independent. There's definitely some overlap. So if you're trying to figure out whether or not you should make a gamble, you might consider some of the counterfactuals. And that might get you out of having falling prey to a gambler's fallacy, thinking about what would have happened if you had invested money in something that you didn't invest money in. So that would be an example of counterfactual reasoning, which might work you away from a gambler's fallacy? It's a good question. Other things like moral or normative reasoning, we're going to talk about this again when we talk about decision making. We'll talk about normative reasoning. We won't talk so much about moral reasoning, but moral reasoning is using some of these other aspects to try to figure out what you should do in a certain situation. So most of us face moral dilemmas. Sometimes they're really big moral dilemmas. Sometimes they're small moral dilemmas. Big moral dilemmas meaning like, I don't know, you've probably been in the situation where you've got an essay that you need to write for a class. The instructor has said, by no means should you rely on artificial intelligence to write this essay. But you might feel tempted to rely on some artificial intelligence to help you through. And then you think, well, how much of this is morally okay? Because you might arrive at the determination that, okay, I'm violating one tenet. This class said I should not use artificial intelligence to write my essay, but I also have all of these other things that I need to accomplish. And so should I make a moral lapse in one case in order to allow me to meet other obligations? That's an example of a moral reasoning. And you might think through some of the outcomes of making those decisions. Sometimes that overlaps, with practical reasoning about what to do to achieve a goal. We're going to talk about this a little bit when we talk about problem solving, so means-end analysis. There are lots of ways to achieve a goal. If the goal in this class is to achieve a mark of 80 or above, so you want to get a good mark, there are lots of ways to achieve that. Some are morally better than others, but there are multiple ways to achieve that goal, and that might be an example of practical analysis. We won't talk so much about spatial reasoning, but spatial reasoning would be an example of thinking about either small space or large space. And sometimes navigation and how different concepts affect our navigation. I mentioned a couple of weeks ago at the beginning of the class that I wouldn't be around during the February break because I was going to go away. So I traveled to Mexico for a week, which was fantastic. And as soon as I got back, everybody said, oh, did you run into any violence while you were down there? And I was like, well, it's a 6-hour plane ride away. It's a long distance. It's a completely different part of Mexico. But most of us have an understanding of geography that kind of lumps things together. Right? The same way that if you meet someone who hasn't traveled to Canada yet, they might assume that it's a lot colder. They might assume different things about Canada. How many of you have traveled outside of Canada, met someone and you say you're from Canada and they assume that you're French speaking because you're from Canada, regardless of where you're from. So sometimes we make those assumptions based on geography. We do spatial reasoning based on large space and conceptual space rather than actual space. Temporal reasoning involves reasoning about time, and meta reasoning has to do with calibrating your own confidence in your reasoning ability. Some of us feel quite confident. We'll talk about that a little bit next week in our ability to reason about things, and sometimes we're confident about our decisions and we're really wrong about our decisions, and we display biases of overconfidence. Okay, does that seem good as an overview for reasoning? And we're going to move into talking about induction. So I'll just briefly describe how it differs from deduction, and then we'll go through some examples. So inductive thinking, today's lecture, has to do with observing things and drawing conclusions based on evidence. This is something that all organisms can do. Unlike some of these other types of reasoning, deductive logic and spatial reasoning and moral reasoning, probabilistic reasoning, inductive reasoning is a fairly basic process. Non-human species have lots of examples of inductive thinking. Inductive thinking is built off of the natural tendency for organisms to generalize. In other words, to observe things in their environment and to try to predict what the outcome should be. So when you learned in your first year intro course or in a course on cognitive psychology about stimulus response association and operant conditioning, what you learned about was how animals learn to generalize. When they see a certain when they hear a certain sound or see a certain color or a certain stimulus, they learn to predict what's coming next, and they may engage in an action in order to cause something to happen in the future. They're engaging in some kind of inductive process. They're making observations and trying to carry out a behavior that aligns with the prediction. Now, they're not going through it using language. It's a stimulus response association. And our inductive processes are built on top of that basic associative learning system. Deductive thinking requires language. Deductive thinking for humans requires the ability to consider premises and conclusions, and it requires a lot more cognitive capacity. So induction, although you can have complex inductions, kind of happens naturally. It falls out of stimulus response and associations that you might make. Whereas deduction involves a hypothesis that leads to systematic observations. These premises leads to a specific conclusion, and it's a general to specific kind of thinking, where you're trying to make a specific conclusion based on what you know. Induction is the process of using what you know to predict what you will probably observe given some set of features or stimulus. So again, it's based on and built on our idea of association and similarity. Another way to describe it is what we do as thinking is mostly induction. The kind of thinking we engage in on a regular basis is mostly induction. A lot of the examples I used when we talked about concepts and similarity and memory are based on induction. Knowing that I've had a cup of coffee, I mean, if I drink a cup of coffee every single day for the last 60 years, it feels like that. I'm not even 60, but if I have been drinking a cup of coffee every single day for the last number of decades, I kind of know what coffee's going to taste like. I have a pretty good sense of what coffee's going to taste like, and I can predict exactly what it's going to taste like based on all of my experience, right? So that's a kind of basic induction. It's not a fairly complicated form of thinking. So induction is thinking. Most of our behavior is a form of induction. So let's go back to some of the fun stories that might have happened over February break. So what did you do over the February break? Can anybody give me an example of what you did and how it might be a form of induction? So a prediction that you made based on observations, whether this was conceptual or expecting something to be a certain way. What are some predictions that you made that would have happened over the break?
For the Olympics, since it was on, I guess you turn on the TV and assume that all the sports channels are playing the Olympic events.
Yeah. Yeah, so in the past, that's how my experience of watching the Olympics is that I would turn it on and that at any given time during the day, there'd be some random sports event happening, something I wanted to watch, or maybe just something that was on that was a sport I'd never watched before. So based on my prior experiences, I would assume that if I turn on CBC or a sports channel, there should be some Olympics. That's a perfectly good example of an inductive inference. Any other examples?
I like volunteered at the hospital over the reading week as like their mascot.
You volunteered at the hospital as a mascot.
Yeah, like their children's hospital.
The children's hospital. That sounds very admirable, actually. So how did that, where?
Like usually there's like, I don't know, like in my head, it's like bad days or good days where like the kids like hate me or love me. And then like that week, like a lot of the first few kids were like very like excited to see me. So I expected like all the kids after would be also excited.
Okay, so you made some observations. You were a cheerful mascot at the Children's Hospital. Again, very admirable type of volunteer opportunity. And you sort of see what happened on one day, and you kind of predict what's going to happen the next day based on your experience. That's a great example of induction. Any other examples of induction or something you did over the break? You assume, because in the past, when you've gone to a warm place, you were able to get a tan. Did that happen? Excellent. So exactly what you would expect. That's sometimes how we calibrate our inductions, whether it's watching the Olympics on TV, volunteering with children, or trying to get a tan on vacation. You expect something to happen in a certain way, and then you notice to see if it did. And that builds up your set of priors. We're going to talk about priors next week when we talk about Bayesian analyses, but that builds up your expectation. Now you have a concept. You expect a certain thing to happen. And the next time you're in that situation, those observations will be a little bit stronger. When I talk about similarity, I talk about a form of inductive reasoning, right? That if you are familiar with what's inside a pumpkin, you would be familiar with what's inside of other kinds of squash. This is a form of categorical reasoning, which is what we're going to end up talking about at the end of today's lecture. So for induction, inductive reasoning includes sort of two broadly defined kinds of outcomes. One is an inference, and an inference is kind of a specific conclusion. Even though I describe induction as being specific to general, you're often making conclusions about one event at a time, right? You're whether it's turning on the TV on one day or volunteering on one day, getting a tan on one vacation, that's going to be a specific inference. So you've got some generalizations based on your experiences, but on a day-to-day basis, you're carrying out individual behaviors. So you're making individual inferences, just like the individual inference that an inside of a pumpkin or a Hubbard squash might have a certain kind of fiber. But these are based on generalizations. So observations lead to generalizations, knowing what's generally true, and then that helps you make specific inferences or predictions. So inferences are conclusions based on the available evidence. They can be specific to a particular case, or they can be kind of general. They can be applied to a broad series of observations, maybe a whole week's worth of events or a whole class of objects that you start thinking about. One specific inference, this is one that I talk about in the textbook. It's barely even relevant anymore. But I still think the example is a good one because it applies in slightly different ways. So 20 years ago, I didn't write the first edition of the book 20 years ago. I wrote it 10 years ago a little bit. Let's say 10, even 20 years ago, most people, myself included, had landline telephones. In other words, a wire came into your house and hooked up to a telephone. It was like the family phone. How many of you still have a family that has a family phone? In some ways, I think it's a terrible thing that that a lot of people got rid of their family phone because it wasn't something you had to carry around. It was like the household phone. Anybody could answer it. Anybody could call it. You can call anybody from that. The landline household family phone was a great idea. However, the family phone between 4 p.m. and 7 p.m. was usually when people would call to market things, duct cleaning companies, or some spam call or something like that. So junk calls would come in. They would call them telemarketers. People would call you and they would ask you for services or a survey or something like that. It was never anybody you wanted to talk to. And so telemarketers would call between the hours of 4 and 7. It happened a lot in the past. And you probably get this experience with your own mobile device, right? You have calls that come in, and if you don't recognize it, you don't answer it, right? That's how it worked even in the landline era without identification. If the call was ringing between 4 and 7, I just assumed, I made an inference that it probably was some kind of junk call. It probably wasn't a person I was going to talk to. It wasn't anybody calling me to talk. So I would infer that the caller is not worth talking to, and I wouldn't pick up. That's a kind of an inference based on experience. You do it enough, you get enough calls between 4 and 7, and you think, well, nobody ever calls me between 4 and 7 unless they're trying to sell me duct cleaning services. So I'm just not going to pick up the phone. Telemarketers in this case were also making some kind of prediction based on experience, and this would have been probably marketing experience, which is in the average home phone, people would be likely, there'd be more people home during the hours of 4 and 7. Remember, this is before the time when people carried their phone with them. This is the time when there was only one phone per household. You get the best chance of getting somebody at home during the usual dinner hour in Ontario. So don't call at 7 o'clock in the morning. Call between 4 and 7 in the evening when people are going to be there. That's also when most people knock on the door at my home? How many of you have people, well, if you live in a house rather than an apartment, you might get people who stop by to sell stuff door to door. I don't understand why. Anybody would buy anything door to door, but people do come door to door and try to sell things. And it's usually during that time when they would expect people to be home, again, during that dinner hour. So we're both making inferences based on experience, and we're trying to predict what's going to happen. I want to predict who's going to be on the other side of this call without actually having to pick it up. And that's the power of induction. It's trying to predict the future. Induction is a way that we have, and all species have, of being able to predict the future. I don't have to pick up the phone. I can predict who it's probably going to be based on my knowledge, which is kind of a powerful thing. If you think about it, you've got the ability to predict things that you can't see and that you don't have to directly experience based on what you already know. So induction is predicting the future. Generalizations is an inductive conclusion about a whole class or a group of things, and often this comes out with positive or negative associations with social groups or occupational groups. We talked a few weeks ago about different kinds of associations or impressions or concepts that you might have of police officers. And we gave some positive examples, maybe some negative examples. Sometimes it's based on the way in which the police officer might present themselves. And so this might be an example of bias or stereotypes. The kinds of things that the assumptions that you draw about a group of people based on your experience might lead to an incorrect prediction or a generalization that doesn't capture all of the individual difference. We'll talk more about these in other classes. We've already talked about these, but these can often lead to then heuristics. So the inductions and inferences that you make and the generalizations that you draw rely on heuristics like availability and representativeness. But they can also lead you to make mistakes. And remember, one of the things about induction is that it's based on what's probably going to be true, not what's guaranteed to be true. Inductions are usually helpful, but occasionally they give you the wrong conclusion. They might might allow you to draw an incorrect conclusion. Let's straighten my microphone here. Another way to say that is that good information will produce good inductions, and bad information produces bad inductions. This can lead to conspiracy thinking, which is something that I think a lot of us try to resist. How many of you have found yourselves believing, or at least half believing, a conspiracy that you maybe know isn't right, but you think is also a plausible explanation for what's going on in the world? I mean, I'll raise my hand. I'm not afraid to say that occasionally I have fallen prey to conspiratorial thinking. One of the challenges, maybe more so now than 10 or 15 years ago, is there's a lot of information which is directly contradictory. And so you have to determine what information aligns with everything else you know. The more bad information, or just the more information in general that you're presented with, the harder it is to be able to draw good inferences. That leads to these kinds of conspiracies, because conspiracy thinking often tries to present a fairly straightforward or abductive reasoning friendly conclusion, something that seems like it's got to be the right answer. It's the only thing that makes sense with a lot of stuff that doesn't make sense. Induction is a natural process, and that's one thing that I try to emphasize throughout today's class. It's something that happens naturally. You don't have to try to carry out inductive thinking. In fact, you can't resist carrying out inductive thinking. Inductive thinking is naturally the way in which we make predictions and generalization. We always generalize from new experience. So if you're overwhelmed with dubious information, information that might not be accurate, information that is based on conspiracies, then you're probably going to make conspiracy-minded inductions. If the information that you have in front of you is information that's inaccurate or that's deliberately inaccurate, then you might draw conclusions that are not an accurate picture of the world. They're based on inaccurate information. We usually call this gaslighting, right? Where a lot of information causes you, or a lot of things that you're getting are encouraging you to think oppositely of what you might naturally draw. Predictions might be false, but to your brain, they're acceptable. And that's the big challenge. A lot of times, you might make the wrong conclusion. You might draw the wrong conclusion, but you're not doing it out of a place of active ignorance. You're not doing it from a place of active error making. Your brain thinks it's making the right decision. From your brain's perspective, if it gets wrong information, it draws conclusions based on wrong information. So conspiracies can be difficult to resist because they seem to provide clear explanations for things that are fairly complex or maybe difficult to understand. Another way in which this comes out is in our tendency to draw conclusions from categories. So we talked about representativeness. So you may be familiar with this paper. I've talked about this before, and I'll talk about it in a subsequent class as well. But let's talk about the primary study. This is work that Tversky and Kahneman carried out in the early 80s. So Kahneman's name has come up a lot in this class. Daniel Kahneman is the one who wrote a book that I talked about earlier on thinking fast and slow, and has been heavily associated with this sort of fast system 1 and slow system 2 way of approaching things. System 1 being a fast kind of inference, a natural stimulus response association, and system 2, one that requires a little bit of thinking. This has to do with intuitive reasoning, and they refer to something called the conjunction fallacy. The conjunction fallacy in this case is reasoning based on what you know about people, what you've observed about people, and then making an error from that. So in Kahneman and Tversky's study, they presented their subjects, their research participants, with a lot of little vignettes and descriptions of people. Here are two of them. In the first one, they designed these to sort of bring to mind a certain stereotype, a certain kind of generalization. We saw this already a few weeks ago when we talked about the stereotype of someone who might be a librarian versus a farmer. Same idea. Bill is 34 years old, intelligent but unimaginative, compulsive and generally lifeless. In school, he was strong in mathematics but weak in social studies and humanities. So this is supposed to make you think of a certain kind of person, fairly or unfairly. It draws on your stereotypes of a certain kind of person. And then you're asked to say, how likely is it that he belongs to one of these categories? In other words, for all of these statements, rate the probability. In other words, is it a really high probability that Bill fits into that group, or is it a low probability? A physician who plays poker for a hobby. I don't really have a good sense about what that kind of person would be, but I don't really feel like Bill is one of those kind of people. Bill is an architect. Well, maybe. Sounds sort of like an architect. Bill is an accountant. This is labeled with A because this turns out to be one of the crucial items. And most people would say, okay, I think probably this intelligent, math-strong, compulsive, unimaginative person would probably make a good accountant. No criticism towards people who are interested in accounting, but this is supposed to evoke a stereotype of someone who'd be really good at math, maybe make a really strong accountant. So people in this study should rate that as a fairly high category. Membership, playing jazz for a hobby sounds like something that is not lifeless. That sounds like somebody who's full of life, right? I mean, if you play jazz for a hobby, that's a lot of fun, right? That sounds like a fun guy. And we're led to believe that Bill is not a very fun guy. So this should be high, this should be low, and then the other critical one is an accountant who plays jazz for a hobby. And what people are supposed to understand is that if you've got a probability of belonging in one group and then a low probability of belonging in another group, when you combine them, it has to be lower because it's a conjunction. In other words, the likelihood that he's an accountant who plays jazz for a hobby cannot be higher than either one of these. Does that make sense? If he doesn't play jazz, he can't be a jazz playing accountant. And another one that comes up, this is probably the one that's a little bit more familiar to a lot of you. Linda, 31 years old, single, outspoken, and very bright, philosophy, deeply involved with discrimination and social justice, participated in demonstrations. So this is sort of a social justice advocate. This is a type of person who would show up at protests, right? You kind of get a sense of what this kind of person would be. And you would endorse very strongly that she might be active as a feminist, maybe not so much that she would work in a bank, particularly as a bank teller, though anybody could work as a bank teller. It's not a category that has a lot of coherence to it. And you would then be asked to say a bank teller who is also active in the feminist movement. And what you should say, if you were keeping track of probabilities, is that this would be lower than either one of the two, right? Because a conjunction of something has to be lower. If she's 85% likely to be a feminist and only 15% likely to be a bank teller, the combination of those two is going to be lower than either one of the constituents. As the reader has probably guessed, the description of Bill was constructed to be representative of an accountant and unrepresentative of a person who plays jazz for a hobby. The description of Linda was constructed to be representative of an active feminist, unrepresentative of a bank teller. We expected the ratings of representative to be higher for the classes defined by a conjunction of attributes than for the less representative constituents for each conjunction. In other words, they expected people to make an error. A group of 88 undergraduates at UBC ranked the 8 statements. The results confirmed our expectations. The percentages of respondents who displayed the predicted order, accountant, accountant plus jazz, and jazz for Bill, and feminist, teller for Linda were 87% and 85% respectively. In other words, people were making inductions and generalizations based on what they thought this person would be like, based on their stereotypes, not based on what their understandings of the laws of probability and conjunction should be. So the conclusion that was drawn by Tversky and Kahneman is that when there are two kinds of ways to reason, a fast way, which is inductive, based on stereotypes, and a slower way, which would rely on understanding base rates and understanding probability theory, we go with the fast way. We go with the way that seems to make the most. We go with the way that requires the least amount of computational effort and is much closer to induction than it is to probabilistic reasoning and deductive reasoning. Another way in which we often see inference is in hypothesis testing. So taking what you know, and this is a form of induction that also aligns with that abductive reasoning that we talked about. Hypothesis testing is where you kind of know what might be happening. Maybe you develop a conclusion about something, and then you devise a test to determine whether or not your understanding is accurate. Some of you in your examples hinted at that, where whether or not you're volunteering at a hospital and expecting children to treat you in a certain way, turning on the TV and expecting to see an Olympic event, or showing up at a beach or a pool in Mexico and expecting to get tan, you can test that hypothesis every day, right? You can turn on the TV and see if the Olympics are on. And that allows you to test your hypothesis and to see if your reasoning is accurate. So a hypothesis is a set of beliefs about the world that can be tested. So you can state it, you can test it, you can devise a test. And inferences can then be verified with additional evidence. We do this all the time in everyday thinking. Those 3 examples that you all gave are great examples of making an inference and then testing that inference through a hypothesis test. Scientific thinking. How many of you are planning to do or are doing an honors research thesis in psychology or another program? So if you're in the thesis program this year, you're probably working on your thesis project now, hoping to collect enough data to be able to present your poster. If you're doing a thesis next year, It's the same thing. You're trying to formulate a hypothesis, design a study that helps you test that hypothesis so that you can understand something about the world. A number of years ago, first house that we owned in London, not surprisingly, had a leak in the basement, which is really common in this part of the world because there's a lot of factors in London, Ontario, which lead towards having leaks in your basement, right? Depending on where your house is located, how the age of the house, and so on. And we bought a house in London, 2003, when we moved here. And the very first winter, sometime around this time of the year in 2004, a couple of months after we purchased the house, the first thing we noticed as I went downstairs, it was a split level house, so it was a finished basement, which was an office. Stepped onto the carpet and my feet were wet. And I was like, I just don't want to have to deal with this today. This is the last thing I want is the basement to be leaking and the carpet to be wet. So it's not something that I was happy about. So it was a process of having to develop some hypothesis testing, right? What is causing the leak? There's lots of ways you can check first. The first thing you can look for is to see something obvious. Did somebody leave the water on somewhere? Number two, was the sump pump working? If you live in a house that has a basement, there's often a sump pump that pulls water out from below. That was working. Lots of other places. It could have been a crack, could have been a frozen pipe because it was in wintertime, could have been a crack in the foundation that water. There's a lot of things, some of them more dire than others. Crack in the foundation, very dire. Cracked pipe, pretty dire, but not as bad. Ice dam that's leaking, could be either way. So we did what anybody would do. We called somebody to look at it because I'm not going to be able to fix this myself. So I called someone who specializes in leaking basements, and the contractor formed an initial hypothesis. The water is coming from a crack in the foundation. That's not what I wanted to hear because that's the most expensive and most unhappy form of leak in the basement that you could have from my perspective. So we had to devise a test. There was a place where you could crawl into a crawl space that was on the same level as the basement. If there was water in the crawl space, then it might have indicated that there was a crack underneath in the foundation because the whole ground floor would have been flooded. The alternative was that if there was no water in that section of the basement, then maybe it was just coming in from the finished section, which would have been a different set of solutions. So we devised a test. I sent him into the crawl space. He found no water in the crawl space, meaning that we updated our priors. We updated our information. We then made some additional conclusions. We looked for alternative explanations. In this case, a melting ice dam. If you've ever seen, how many of you live in homes that are near campus, walkable distance from campus, like in the Brofdale area or something like that? How many of you have massive icicles on the side of your house for your student rental house? That's an ice dam. That means that the ice just keeps building up and it holds up stuff behind it, and the ice gets thicker and thicker. Well, eventually that ice has to melt, and occasionally it's such a big ice dam that the ice melts inside the foundation or inside the house. It doesn't necessarily mean there's anything wrong with your home. It just means that the water has to go somewhere. Sometimes it goes down, but sometimes it comes inside the house and finds its way into the basement. And that's what caused this leak in the time. But it required some hypothesis testing. We had to decide what could be an explanation, what's a likely explanation, and then let's test the likeliness, the veracity of that hypothesis. So this is a combination of inductive reasoning and abductive reasoning, trying to figure out what's the best explanation for what we're seeing. I'm going to talk for the next does your attention span feel like it has 10 more minutes? Okay, let's talk for 10 minutes about correlation and cause, and then we will take a short break and talk about categorical induction. Does that seem okay? So we'll get through the causal correlation stuff. We're going to come back to this next week anyway. Take a little break, come back. We should be able to finish up by noon. So in the large list of kinds of reasoning. We talked a little bit about causal reasoning. And we also talked about abductive reasoning. We talked a little bit about trying to go back and think retrospectively when you're thinking about what might be causing something to happen, or what might be an appropriate explanation or prediction. A lot of that has to come from thinking back, retrospective designs, sometimes using counterfactual reasoning, thinking about what might have happened even if it didn't. A lot of what we know about the relationship between the environment and human health comes through these sort of retrospective epidemiological designs. So, antibiotics, for example. There was a time a few years ago, maybe about 10 years ago, when there was a study released, a study was published, that showed a correlational relationship between the assignment of antibiotics younger in age and the tendency to develop breast cancer later in age. And so the question is there a causal link? Is there some relationship between a certain kind of antibiotic which might cause a certain kind of cancer? Or is it that something else is causing both of those things? In other words, some immune function which might early in life result in more infections that require antibiotics, that later in life also results in a susceptibility to certain kinds of cancer. You can't tell which one of those is the best alternative looking retrospectively and looking at correlations. So correlations can show you the relationship, but it makes it harder to determine what the cause is. Most of you probably have heard about relationships between aluminum and the development of Alzheimer's disease. How many of you have heard of this possible link? It's not as widely discussed as it used to be because there's no truth to it, or there doesn't seem to be any truth to it. But how many of you have purchased natural deodorant that says aluminum free? Have you ever seen this? Tom's of Maine natural deodorant, which is the kind that I use, says aluminum free. Why does it matter that it's aluminum free? Does anybody have a good explanation why you would want to advertise deodorant as being aluminum free? Anybody have any idea?
They're kind of assuming that people are worried about aluminum in their deodorant.
Yeah, I mean, like, why would you be worried about aluminum? I have no idea why you would be worried about aluminum in your deodorant, given that aluminum is what all of your cans are made of. It's what most cookware is made of in restaurants. Aluminum is one of the most abundant metals, elements on the planet. It's not an uncommon thing. So just having it in deodorant hardly seems like it would be a cause. There was a time when there was a relationship possibly believed to be between aluminum and Alzheimer's disease. And one of the reasons was that the way in which certain staining was done on brain slices as they were in a study that was looking at brain changes in Alzheimer's, detected what seemed to be more aluminum in the brain. There's no causal relationship, but at the time, the reaction was, well, we should reduce exposure to aluminum. Don't use aluminum cookware, even though most restaurants do. Don't use aluminum in your deodorant. And so that just it's kind of a legacy. Now just some deodorants say aluminum free, even if there isn't a relationship between aluminum and Alzheimer's disease. Whatever it is that ultra-processed food does to your physiology is likely going to be something that can only be analyzed through retrospective designs because it's too complicated to isolate these things. You used to hear a lot about autism causing, or vaccines causing autism of a certain kind. Then that went away, and in the United States, that's come back again, whether or not childhood vaccinations cause autism. We'll talk more about some of these relationships next week when we talk about Bayesian reasoning. Retrospective designs look backward to examine causal factors, and as we'll see in next week's lecture, it also represents a form of a logical error, a reasoning error. That's why most of us who are thinking about carrying out an experiment or testing a hypothesis try to look forward and design a hypothesis test. You know what a correlation is. You probably learned this long before you started university. And you certainly, if you're studying psychology, would have learned about correlational designs in your intro course, in your second year stats course, and in other courses. So we all know what a correlation is, and that means that it's a relation between two things that you can measure, two variables, two constructs. Positive correlations mean that if one thing increases, the other thing increases along with it. They are literally correlated, right? That's what a correlation means. A negative correlation means that if one thing increases, something else decreases. Those are two kinds of relationships, but lots of things are related even if there's no reason for them to be. And that's because cause and correlation are in fact correlated, right? Causal things that are causally related, tend to be correlated. But lots of other things can be correlated which don't have a causal relationship. So it's natural for your mind or your brain to assume some kind of causal relationship when you notice a correlation, because it's something that lets you know that there's a causal relationship. The problem is that you can overdo it, right? You can overgeneralize a correlation. You can overgeneralize your understanding of correlation to infer or understand causation when there isn't any. And you can find hundreds of examples like this. Cases where there are correlations, very strong ones, very strong relationships between two variables, which can't really have any actual causal link. The popularity of the first name Johnny correlates with burglaries in the US state of New Hampshire in a really weird and sort of unsuspectingly close way, such that in the 80s and 90s, there's a lot of Johnnies out there. And as Johnnies go down, so does the burglary rate. Milk consumption and divorce in Colorado, again, a very strong relationship. They both go down together. The popularity of the first name Kenzie, anybody named Kenzie, apparently goes up and down in a strongly related way with UFO sightings in the US state of South Dakota. So if your name's Kenzie and this is when you were born, there were also a lot of UFO sightings around the time that you were born. Coincidence? I think not. So it tends to be something that we understand is not right. Most of us understand correlation and causation are linked, but they can't be inferred. So much so that it's probably a bit of a cliche to say you can't infer causation from correlation, right? I mean, it's almost a cliche. The problem is that that's what it was designed for. And I think this is where a lot of it becomes really difficult. Even though most of us know, so much so that it's a cliche, that you cannot infer causation from a correlation, we usually do still think about it that way. A lot of us still think about correlations as being causal. Even if we know we shouldn't, it's natural to do so. There's two reasons why. First, that's what it was designed to do. So Pearson's correlation coefficient was designed to be a better measure of causation. Pearson writes, the higher the correlation, the more certainly we can predict from one member the value of the associated member will be. In other words, if it's truly correlated, it would be close to causal. This is the translation of correlation into causation. So what Pearson was trying to do was to come up with a measure that gives you some degree of confidence that two things that you measure are not only related to each other, but that might have a causal link. That doesn't mean that it's the only possibility, but it gives you some way to evaluate the strength of the relationship such that the stronger the relationship is, the more likely it is to be based on causality. Doesn't mean that there aren't alternative explanations, but it's one thing. Correlation doesn't prove it, but it is kind of a necessary condition. So when we're thinking about causation, they are usually things that are also correlated. The other way to think about it is that causally related things, here's a group of things that are causally related, are a subset of the things that are correlated. Causally related things are correlated, but not all correlated things are causally related, if that seems clear. And so most of us go through life thinking we know that you shouldn't infer causation from correlation, but also still doing it anyway, because that's the way your brain seems to work. Okay, let's take a break. This is a great place for a break because now we're going to go into some philosophy and talk about David Hume's problem with induction. And then we'll talk about categorical induction for the rest of the class. So it's about 10:38. How about 10 to 12 minutes? And as soon as we're all back, we'll just continue.
Gonna check right now. I don't mind just mindlessly taking. I'm not against it.
Wait.
All right, it looks like we're all back, more or less. I kind of feel like the density of people to seats is about the same as it was before the short break. So let's continue.
Yeah, I'm gonna. I'll consider it. It's like absolutely. I go back from five, so I can adjust the words and.
Okay, so we talked about reasoning and induction in kind of general terms. Let's talk a lot more about what induction is, how it describes human thinking, and then we're going to talk about two different theories of deduction that are based on the idea of categorical reasoning, that you reason from concepts and categories. So I set this up in the textbook as well. And the reason I like to start with the philosophical underpinnings of induction is that it helps to describe why we should treat induction as a category and concept problem rather than just memory in general. So to do that, we're going to go back to David Hume, who's a philosopher from the Enlightenment era, and then talk about two additional philosophers from the 20th century who addressed this same problem. All of these examples identify induction as a natural byproduct of how the brain and mind work. So starting with Hume's problem. David Hume, who lived in the 1700s, was a Scottish philosopher. And this is fairly small text here, but in 2009, he won first place. I don't know what kind of contest this is. In 2009, he won first place in a large international poll of professors and graduate students who were asked to name the dead thinker that they most identified with. So I guess most people, when asked to identify which dead philosopher do you identify with the most, Hume comes up as the top of the list. So he's everybody's favorite dead thinker. And he thought a lot about induction. He thought a lot about other things too, but induction is one of the things that he thought the most about. And it's one of my favorite examples from philosophy that underpins some of the thinking psychology we're going to talk about. So was worried about whether or not induction was even possible to study. And the reason he was worried about it was that at the time philosophers studied deductive logic. And deductive logic can be studied formally. And by formally, I mean that you can develop a system of thinking about deduction, whether it's truth tables or syllogisms. You can study a system of thinking deductively, but it's harder to do that with induction. And I want to draw your attention to what I'm going to refer to as Hume's negative thesis and Hume's positive thesis. These are two ways that he was concerned about induction. I'll describe them on the next two slides in slightly different ways, but this is how Hume describes it. We cannot hold that nature will continue to be uniform because it has been in the past. So think about what that means. So what that means is that we can't assume that the future is going to resemble the past. Everything that you have, that you reason from, is happened in the past. We don't know what's coming next. Now, I already said induction is trying to predict the future, right? So that's what he's worried about. If you're going to predict the future, you have to base your predictions of the future on your understanding that the past has been consistent. If, for example, every time you turn on the TV during the Olympics, there's Olympics on, and that's happened in the past, you would assume in the future that would happen. But how are you going to know? You don't know what's going to happen 2 years from now. You don't know what's going to happen 2 seconds from now. So we don't really know if the past and the future are related. We assume that they are because they mostly are. But things change, right? So he says we cannot hold that nature will continue to be uniform because it has been in the past, as this is using the very sort of reasoning that is under question. It would be circular reasoning. And what he means is that if you assume that the future resembled the past in the past, you would then assume that the future would resemble the past in the future. That's using induction to solve the riddle of induction. And that's what he's concerned about, that if you base inductions on the assumption that the future will resemble the past, and that's worked in the past, you can't know that that's going to work in the future because you're using induction to understand induction. And so he's worried that you're not going to be able to understand anything. That induction doesn't make sense, that it can't be studied. And I'll show you 2 other examples which are equally confusing, but try to make the same point. So Hume is saying that just because the future resembled the past in the past, we can't assume that the future is going to resemble the past in the future. In other words, the future past might not have a relationship with the future future the way that the past past had a relationship with the past future. I realize it sounds like I'm in the middle of a SpongeBob SquarePants episode when I say that, but you kind of understand what I'm saying, right? Things were consistent in the past. We assume things are going to be consistent in the future, but that is an induction. And if that is an induction and we can't know that that's going to happen, then how can we know that any induction is going to happen? And Hume kind of threw up his hands at the time and said, you know what, maybe we just have no choice. Nature, by absolute necessity, has determined us to judge as well to breathe and feel. In other words, Hume says, I don't know how to explain induction either. And I recognize that it's sort of a logical challenge for me to explain how induction works, but maybe we just do it anyway. Because if we didn't have the ability to try to predict the future, we would be hopelessly lost in the present. And so his suggestion is, look, it's just nature's way, right? It's part of the plan. I don't know why it's there, but we breathe, we feel, and we judge. And by judge, he means judge things about what might happen. In other words, we make inductions. So in years past teaching about this, in the past, I know that that particular description has sometimes been a challenge to distinguish between positive and negative. So I reworded them. Hume's negative thesis. I feel negative because induction cannot be explained without resorting to induction itself. And this is a major problem for philosophy. That's what he's saying with his negative thesis. So that's a mnemonic for how I would remember it. His negative thesis is, I'm feeling really negative about induction because it means that it's a problem for philosophy. If I can't explain it using philosophy, then this is a problem for the field that I'm in. So I'm feeling kind of negative today about it. But then he says, you know what, look, maybe it's a problem for philosophers. I'm feeling kind of positive about it, but it seems to be the way of nature because without induction, we could not survive. So I feel positive now. I feel better thinking about it. I can't explain it, but who said I should be able to explain everything? It just seems like this is how the world works. So I was feeling negative about it, but you know what? Without it, we couldn't survive. So I feel pretty positive too. That's what he's trying to say. I can't explain it in philosophy. There are some challenges here, and that's going to be for people in the future to solve. But I'm feeling positive about it now, and it seems to be natural. So what he's saying is, this is the way things work. And that's what I've been trying to say too. This is the way your mind works. It makes inductions whether you want it to or not. So later, many years later in the 20th century, a philosopher named Nelson Goodman published a paper called The New Riddle of Induction. Unlike Hume, Goodman was not willing to let this go and basically said, look, it is still a problem for philosophers. And as a philosopher, rather than making things clearer, he made things less clear with a thought experiment. And here's Nelson Goodman's thought experiment. So imagine you are an emerald examiner. Your job is to examine emeralds. And what color are emeralds? They're green, right? Because that's the name of a color, emerald green. The Emerald City is green because it is made of emeralds. So we understand that emeralds are green, and your job is to examine them. And you see green emeralds. And as an induction, you would say, well, I have seen green emeralds. All emeralds are green. I mean, that's just a property of emeralds, right? Every time I've seen one, my experience tells me that it's green. This is a green, this is a green, this is a green one. What Goodman says is that that's fine, and that maybe that's how you want to work. But I'm a philosopher, and my job is to make things more difficult. What about the property of GRU? Have you ever thought about GRU? GRU is, rather than saying all emeralds are green, GRU is a property that means all emeralds that I have seen so far in my life up to this very moment have been green, and everything that I haven't seen yet, in other words, all future emeralds, just for whatever reason, are going to be blue. Like there's no way that I could know that that's just the distribution that I've had. But for 20 years, I've been examining green emeralds. And the next thing you know, I'm going to examine a bunch of blue ones. And everything from here on in is going to be blue. Now, that doesn't sound realistic, but you can understand how it's technically possible, right? If there are millions and millions of emeralds in the world, there's a finite number. And just by chance, you happen to see all the green ones first, and there were some blue ones out there. And at this very moment, you're on the precipice of now having to examine all the blue emeralds, but you didn't know it. You would be in the state of GRU, which is everything I've seen is blue, and everything I haven't seen everything I've seen is GRU. All the ones that I haven't seen, I said it wrong again. All the emeralds thus seen are green, and all not seen and blue means that all emeralds are GRU. So what Goodman says is that at any given time in your emerald examining career, these two properties are simultaneously true from your perspective, right? It could be that all emeralds are green, and you've gone through life examining 20,000 emeralds, and they've all been green, and the next 20,000 will all be green at this moment. And it's also true from your perspective here that everything you've seen, all 20,000 have been greenish to you, but the reality of emeralds is that they're GRU. You're going to start seeing blue ones from this very moment onward. You have no way of knowing at this moment which one of those two properties is true, because they're both simultaneously true, but they make opposite predictions. And so Goodman's question is, how do we know which one of those two properties to trust? If we know that the future will resemble the past and everything's going to be green, or if we say, well, the future does not resemble the past from here on in, but from my perspective right now, they can both simultaneously be true. Which one of them do I trust? And furthermore, why do we trust this one and not this one? Yeah.
Would this framework contrast Plato's essentialism?
How so? I don't know.
Like Plato's basically that we're in an imperfect world and there's a perfect standard. And so what I'm thinking here is
Yeah.
everything is green, but there could be a blue, right? So
that's a really good observation. So if there's an ideal, on a Platonic ideal, our job is to discover what that ideal is as learners in the world. And here, at some point, we don't know what the true state is. And so that might be a good way of thinking about it, is that for GRU, the true state is there are green and blue emeralds, and you just happen to see all the green ones first. And you'll see all the blue ones next. It's a little different from that, because what Goodman is saying is that GRU is a constantly changing property of at any moment in time, they could all shift to being blue, and I don't know what that's going to be. So GRU is very specifically defined as everything I've seen is green, and what I haven't seen is blue. But it gets to this larger idea that there is sort of a truth out there. And your job is to determine what it is. So what Goodman is concerned about is induction cannot work. If we're making inductions, how does it work? So he wasn't willing to just say it's nature. What he's saying is, fine, Mr. Hume, it's nature, but how do we decide that this is the nature we're going to understand, and why don't we choose this nature? Because at any given time, they're both true. And if they're both true, we've got to decide which one to make our inferences from, and none of us make our inference from this one. Even if we're told that it's kind of true, we don't make that inference. Does that make sense to everybody? So green and GRU are true at any given moment in this thought experiment, but we don't make predictions based on GRU. We make predictions based on green. So Goodman has some solutions. Goodman says, well, one possibility is that we don't make inferences unless the concept or the property is entrenched in our culture and our language. Entrenchment means that a term or a property or a description or a feature must have some past history of use. In other words, you must know something about green as a property that can be described to a lot of things, trees and frogs and emeralds. They can all be green. So it's a property that things can have. So it's entrenched in your language, it's entrenched in your culture, and it's entrenched in your description of the world. GRU is very specific to this particular thought experiment, and it doesn't extend beyond that. And this should remind you of some of those basic color terms that we talked about. Green is a basic term. It describes things, whereas GRU describes a certain state of affairs that only exists in this one example. And so we make our inductions based on things that are culturally and linguistically entrenched for us, and not on things that are sort of a novelty in this case, even though it's true. We're not saying that GRU isn't true, it's just not something that's entrenched. Another philosopher, W.V. Klein, suggested even further that beyond entrenchment, we make inductions on things that he called natural kinds. Natural kinds is a philosopher term that might align pretty well to what we would describe as a category or a concept. A natural kind is something that groups together naturally. Green emeralds form a kind. Whether you've seen them or not, they form a group of things. In fact, if there was a case where emeralds were GRU, and you saw a bunch of green ones, and then suddenly you started seeing only blue ones, you would probably just form a new kind, wouldn't you? You would say, these are blue emeralds. And so I have now seen green emeralds and blue emeralds. You wouldn't call them GRU emeralds, things that I've seen and green and not seen and blue. So what Quine says is we don't form inferences based on these kinds of temporal logic or things that might depend on observations in certain times. We form concepts based around natural kinds. Green emeralds are a kind held together by similarity, a color. GRU emeralds do not have a similarity structure. There wouldn't be anything about GRU emeralds, that is to say, everything I've seen up to now, because that property changes every time you pick up a new emerald, right? Each time you pick up an emerald in Nelson Goodman's experiment, GRU changes. It's now everything I've seen is green and the next one is blue. I got another green one. They're still GRU though, because the next one could be, so it keeps changing with time. That's not a concept. That's not a natural kind. And this works well because animals make use of similarity all the time with primitive features. And we have theoretical kinds of similarity. We had a whole class on similarity. And so what this should suggest is that induction, as we know it, the kind that Hume says we naturally do, should be categorical for the most part. We should make our inferences and our inductions on concepts and categories. That's why the term green is entrenched, because green things, it's a feature, right? It's a thing that is a group. It's a category of things. Reliable inductions come from categories. And as we'll see at the end of today's lecture, the more coherent and tightly bound a category is, the stronger the induction. We form inductions based on how strong a category is and on how similar things are. Apples and pears are kinds. So if you know something about an apple, you might be able to predict it based on a pear. They're not similar exactly, but they're members of the category of fruits that come from a tree that you can eat in your hand. So apples and pears might be kind of similar. Apples and red balls that are of the same size really aren't a kind. Even though they have some surface feature similarity, you don't expect to eat a red ball. You don't expect to find seeds inside of a red ball. So we know what forms a natural kind. Apples are kinds, pears are kinds, and they're part of a larger category. Apples and red balls, not part of a larger category. So Hume, Goodman, and Quine all work together to suggest that we make inductions naturally, but when we do so, we base our inductions on concepts and categories that are held together by similarity. So we'll call this categorical induction, and we'll talk about categorical induction for the rest of today's class, but we'll talk about it in different ways. So we've already described a concept and a category as a behavioral equivalence class, and induction is one kind of behavior. So it's a class of things. We behave towards it in the same way. Categorical induction involves generalization, similarity. Concepts are organized by similarity, and predictions are based on conceptual similarity. The more alike things are, the more likely you are to trust your inductions. So let's talk about how you set up an experiment to study. So I want to talk about this as the way these experiments are set up, because we're going to use these examples for a lot of the studies we're going to talk about and a lot of the theories we're going to talk about. A categorical induction is, how do you arrive at some kind of confidence that a conclusion that you're going to make, a conclusion category or an induction or a generalization, has some feature or predicate after being told that some premise categories do. In other words, once you're told that apples have a certain property, how likely is it that pears will also have that same property? I mean, it's either yes or no, and there's some degree, right? It either has a property or it doesn't have the same property. And sometimes you're really sure that it does, and maybe other times you're less sure that it does. So there's some confidence there. So you're taking what you know about an object, determining whether or not objects in that category have that property, and then determining whether something else that might be related also has that property. So how many of you study cognitive neuroscience or study neurochemicals or neurotransmitters? So GABA is a neurotransmitter. Does anybody know what GABA does as a neurotransmitter in the brain? Great. Oh, you do, but most of us don't. What does it do?
Inhibitory.
So it has some inhibitory mechanisms. So if most of us don't know what GABA does, but we also know that it's a neurotransmitter, that means that it's kind of a blank predicate for us. It's a feature that we kind of know a little bit about, but we don't know a lot about. And if you're told that boys, male juvenile humans, use GABA as a neurotransmitter, how likely is it that girls use GABA as a neurotransmitter? You would probably say, yeah, probably, because based on what you know, even if you don't know what GABA does, and you don't know how it aligns in male and female, biological male and female brains in humans, you probably also understand that the neurochemistry of biological male and female human brains is really similar. And so if there's a neurotransmitter in one brain, it's probably in the other brain. And you would say, yes, if I'm told that this neurotransmitter is active in male brains, it's probably active in female brains. That's an example of a categorical induction. Because we know one fact, we can predict the other fact, because these two things, male and female brains, are in the same category. They're very similar to each other because they're both human juvenile brains. We call this a blank predicate. It's a feature that you know something about, but you don't know a lot about. And so the neurotransmitter, and later we're going to see some examples on the next few slides of sesamoid bones. How many know what a sesamoid bone is? Anybody know what a sesamoid bone is? Okay, a few of you do, but most of us don't. But we know what bones are, and so we can just say, well, that's a kind of bone. I don't know what it does, but it's a kind of bone. These are blank. You kind of know a little bit about them, but you don't know a lot about them. So it's crucial in studying categorical induction because it ensures that when the participant in the experiment or in the study makes a conclusion, they're basing it on induction and not just memory retrieval. It's not really an inductive inference if you just retrieve a trivia fact, right? That's not induction, that's memory retrieval. We want to study how do people discover something new by thinking? How do they make a prediction based on what they know rather than how do they just remember a fact? So here's a couple of examples, and we'll come back to these. We'll actually look at some of these examples later, but scan the code or click the link and just answer the questions based on what you think is the most likely. There's no right answer for any of these. Just do it quickly. The responses, I'll wait another minute. Probably flip back and forth between this and some of the answers on the slide. So it's okay if we don't have everything. We had 66. Let me just refresh and we'll stick with this. So let me make this a little bigger here. Okay, so which of these arguments is stronger? This is a really easy one. Robins have sesamoid bones, therefore sparrows have sesamoid bones. So I don't know what a sesamoid bone is, but most of us think that if robins have it, sparrows probably have it too. And if ostriches have it, we're less likely to think that sparrows have it. So the first one seems like a stronger argument. And by argument, I just mean a stronger inductive argument. So why is that? Why does
Because they have more, robins and sparrows have more like surface level similarity than
they
ostriches.
got a lot of surface level similarity. They're both really highly typical. They're similar to each other, and that's going to end up being the important thing. As you said, they have features. So they're similar to each other. The ostrich is kind of an outlier. Why wouldn't ostrich also be a good example here? Well, you might say, well, it's kind of an unusual bird. Maybe there's something about sesamoid bones that are important for ostriches which don't fly. And if you had those bones, maybe you wouldn't be able to fly around. So maybe it's big, strong leg bones or something in the ostrich, which the sparrow doesn't have. So I would think that that makes like a perfectly sensible inference. Robins and sparrows, different species, of course, but they kind of seem similar. If they're similar on the outside, they're probably similar on the inside. And so you're predicting, just like the pumpkin and Hubbard squash, you're predicting something you can't see. I cannot see what a sesamoid bone is in this case, but I know that if one has it, the other one probably does, and it's based on similarity. Another one here. So which of these arguments is stronger? Robins have it, therefore all birds, And we're drawing the same conclusion. Now it's not just a specific conclusion about sparrows. We're generalizing to the entire bird category because robins have a lot of features that other birds have. Most of us kind of think of it as sort of a prototypical bird. If it's sitting in the middle of birds' space, the conceptual space for birds, and it looks on the surface, on the outside like a lot of birds, it probably looks on the inside. Penguins are unusual, and so we would be less likely to draw a conclusion. This is a forced choice. You might think that either are perfectly defensible, but one is a little stronger than the other, and that's the one that we've chosen. Here's one we're kind of divided on. Hippos and hamsters love onions. Therefore, all mammals love onions is a little bit stronger than hippos and rhinos love onions. Therefore, all mammals love onions. We're almost divided with a slight preference for hippos and hamsters. Why hippos and hamsters?
We're talking about all mammals having more differences.
Yeah.
Have it better than
So your answer was that, the answer was that hippos and hamsters better represent all mammals because you got a big mammal and a small mammal. If you're going to make an inference about all mammals, you kind of want some evidence that all mammals would have this property of loving onions. And in this case, you got big hippos over here and little hamsters over here. And that seems a little stronger than knowing that hippos and rhinos, which for all intents and purposes kind of seem similar, right? They're both big, lumbering land animals that you would only ever encounter probably in a zoo or something like that. And they don't cover as much of the space. Maybe they're kind of similar to each other, but there's lots of other mammals out there that do not resemble hippos and rhinos. And so you've covered less of the space. So it seems less strong of an inference. Finally, let's come back to this one later. We're going to talk about this one, but here's another one where we're kind of split down the middle. This gives us an example of cats and field mice. Cats and field mice have a parasite. So if you know that cats have a parasite, field mice also have a parasite, then how likely is it that all mammals have a parasite? And we chose about 53%. The alternative is that cats have a parasite, tigers have a parasite, and therefore all mammals have a parasite, 47%. So right down the middle. This is one where it's a little less clear what the right answer should be. If you're thinking about this from covering the entire category space, cats and field mice do a pretty good job of that, right? They're a little bit different, whereas cats and tigers are just this, one's a bigger version of the other, right? So that would align with what you said about hippos and hamsters. An alternative way of thinking of this, and what we're going to show in a few slides, is that oftentimes people might prefer participants might prefer the second. So if you preferred the second, the reason might be that you recognize that there's a causal link. If you understand the causal link between cats having a parasite and field mice having a parasite, in other words, if cats catch this parasite from hunting mice, then it isn't necessarily something that would be projected to all mammals. It might be something that's kind of unique about the cat and mouse game, that if mice have it, cats get it from the mice. Other mammals don't necessarily have it. These are both viable possibilities, one having to do with causation, the other one having to do with large category membership.
kind of that reason. We say this for cats and tigers, as in they're both in the same family with felines. So it's not like necessarily cats and mice like
Yeah.
other, but they're from one group. So instead of saying all mammals, we can say more felines.
Yeah, so that one, that's I think the argument here is that this shouldn't be something that you would want to project all mammals because it's just a feline issue because they're both felines. So this is where it's a little bit of a disconnect. This does not seem like a strong answer, but to the extent that you might choose that answer, cats and tigers, it would likely be because the other alternative, rather than suggesting something that's true for all mammals, is something that's just true for house cats hunting field mice. And there's a causal link there. And I'll show a little bit, some other examples of this causal link. But those are two different explanations that kind of conflict with each other. Okay, so I'll come back to these examples as we go. So that makes it easier for me to go through some of these because we've already done them. So the first one we talked about had to do with sesamoid bones and robins, sparrows, and ostriches. And this is what's known as a similarity-based induction. You make a conclusion based on how similar the premise and the conclusion are. The more similar they are, the stronger the induction. And we all chose the robin sparrow because it's more similar. Robins over here, kind of similar to sparrows over here, not so similar to ostriches down at the bottom. Another argument has to do with coverage, and that was the second example that we looked at, robins and all birds versus penguins and all bird. One of them covers more of the category. You've got robins over here. They cover a lot of bird space. Penguins are a very small slice of bird space, and so if you're making an induction, you're less likely to draw the conclusion. Robin is typical and covers more of the category. The third one we did is called the diversity effect, and this also reflects coverage. The less similar two premises are to each other, the stronger the argument will be. In other words, the less similar they are within the same superordinate category. Hippos and hamsters are not very similar to each other in the mammal category, and so it makes it seem like a stronger argument. I think one of you said that's why you would choose it, because you've got hamsters over here and hippos over here. It kind of gives you a good representation of all mammals, whereas the alternative set of premises gives you a small representation. The diversity example has greater coverage. Finally, and this is one we didn't do, but this builds off this idea of diversity, and that has to do with inclusion and category inclusion. And this is one where most people, or at least the majority of participants in an experiment, would choose an alternative. Which is the stronger argument? All robins have sesamoid bones, therefore all birds, or all robins, therefore all ostriches have sesamoid bones? Which of those two seems like a stronger argument? All robins, all birds, all robins, all ostriches.
The second one, because you're like only one other thing to compare it to.
The second one logically should be stronger because you're only comparing to one thing. But how many of you feel like the first one is still a good answer and would be likely to pick the first one? And in a lot of studies, the majority of participants would pick the first one. If you would want to pick the first one, what's the example? So you gave the right answer for why the second one would be preferred. The second one would be preferred because you're just comparing to one thing. If robins have it, well, maybe ostriches do too. So what's...
I would assume that for the first one, if an individual views like a robin as the most typical member of the bird category, then they would go with the first option that because robins have it, all birds.
We already suggested in an earlier example that if all robins have bones, there's nothing wrong with saying all robins have it. And so the suggestion here is that most participants do prefer that, as we showed earlier, that when you're asked to project a property from robins, you would project it to all birds. But in this particular case, it might be a fallacy because, as you mentioned, ostriches is one comparison. Ostriches are already included in all birds. So if you're willing to draw it to all birds, it should also be even stronger to ostriches alone. In other words, these should be at least equal, and it should be a little stronger for the one that is the unique comparison. This is definitely not this shouldn't be untrue in this case, because if we already think it's true for all birds, that includes all ostriches. Ostriches are included. And this is what's known as the inclusion fallacy. And the reason it's a fallacy suggests that most people, at least in this case, will tend to rely on featural similarity. They recognize that robins and ostriches don't share a lot of features. And by not sharing a lot of features, therefore, they shouldn't project that property. But it undermines the categorical similarity. There's a category inclusion effect. They're both members of the bird category. And if we already agree that all birds have it, then all ostriches should have it too. In fact, it should be more likely. And so this suggests a bit of a conflict between whether or not you rely on knowledge of a category or just individual feature comparisons. That's going to set up a conflict between two theories of categorical induction, which I'll discuss on the next couple of slides here. So the first of these, and I discussed both of these in the textbook, the similarity coverage model and the feature coverage model. Mostly they make the same predictions, but they diverge on the inclusion fallacy. So the similarity coverage model suggests that the strength of an inductive inference depends jointly on the similarity between the premise categories and the conclusion category. So robin and sparrow, those were similar. Robin and ostrich, not so similar. And how well the premises cover the lowest level category that includes premises and conclusions. So by lowest level category, I mean whatever the lowest level hierarchy is. So if you only need to go up one level, all birds, that's the lowest level of abstraction rather than all animals. So whatever category level includes everything that you're talking about, that's the lowest level of abstraction. And so you take into account similarity, the average similarity between premise category and the conclusion category, more similar premises, stronger argument. For example, horses and cows would be stronger than horses and dolphins because horses and cows are similar. That's a strong induction. Yeah.
By lowest, you mean like the most broad?
Yes. So I mean, the lowest is probably a challenging term in this particular case. So I mean the broadest category. I don't mean the most specific. I mean the lowest level as you go up in the hierarchy. So not going to the very top of the hierarchy like all animals, all living things, but what's the lowest level you can ascend in that hierarchy to include everything? That's a good clarifying question. So that's similarity, literally similarity between one concept and the other, and we know how to define that. We've defined that as featural and feature space and so on. Coverage is how well the premise set covers the lowest superordinate category that includes both premises and conclusion. So in this case, all mammals, all birds. That's the lowest level superordinate. Does that make sense? So you're going up the hierarchy, but you want to go up the least amount possible. So the lowest level superordinate. Diverse premises cover more of the space. That's the hippo and hamster, or in this case, horses and dolphins. If you find out there's a property that coexists between horses and dolphins versus all mammals, that's higher coverage than horses and cows projecting to all mammals. Does that seem clear to everyone? So similarity and coverage suggests that we take both into account. And the model would work in the following ways. We might have an argument strength. You're not going to be I'm not going to expect you to work through this formula, but this suggests how the mind might do this. When I present these kinds of formulas, I don't mean to say that you're going to need to work this out. But what I'm suggesting is this is a formal way to explain how humans reason, suggesting that your mind is doing a calculation somewhat like this. You might create some kind of argument strength based on the similarity and then adding to it the coverage. In this case, you might have a weighting parameter which puts greater stock in similarity or maybe greater stock in the coverage. But essentially, you're combining these two things. I've got similarity and I've got coverage. I combine them in order to be able to come up with the argument strength. If I know that horses have enzyme X, dolphins have enzyme X, and therefore all mammals have enzyme X, I would first come up with the average similarity, horses and dolphins, and maybe that's kind of a medium level similarity. maybe a medium level similarity of horses, maybe a higher level similarity of horses to mammals versus dolphins, but the coverage is fairly high. Dolphins and horses are, one's aquatic, one's a land mammal, and so they cover a lot of the space. And that lets me make a stronger induction.
Do sports teams use this model, like draft analysis and like the prediction?
I actually have no idea. That is a great question. How would you do that? So the question was, do sports teams use this for draft analysis?
Like I was just thinking about it, like, let's say hypothetically you have like a college player and you get drafted to the league and like you look at his play styles and everything, you compare that to a previous NBA player, I guess.
Yeah.
You see if that applies that to your team and if he works well with your team. Well, like, that's what I was thinking, like the similarity
Yeah, that's a really good,
and then the coverage would be like the NBA, like
yeah.
the NBA team and the players around it.
All right, I'm going to have to file this away for later because I don't know the answer to that. That is a really interesting question. It's interesting to me how often these kinds of things, like things like drafting in professional sports, apply well to things like decision making and probability theory. So I'm not sure exactly what models you might use. You could easily use something like this, where you understand that there's similarities for a player to other players, but then also the degree to which they've played for other teams and other coaches and have come up with success within a specific league. So that's a really good question. I have absolutely no idea. I'm assuming that it's much more sophisticated than this, but I don't know how it's done. And now I'm sort of interested and intrigued to sort of find out how this kind of stuff is done. Okay, so does everybody sort of get the gist of how the similarity coverage model works? You understand something about the similarity based on your conceptual knowledge, and you understand something about the coverage. And so it predicts things like this typicality effect, which we've already talked about. Typical categories are more similar. It predicts this diversity effect. It produces general things like monotonicity, and all that means is that the more premises you add, the stronger the induction is. Adding more premises to a domain, to a general conclusion argument should never decrease its strength. It always makes it stronger because now you have more evidence. However, for adding a dissimilar premise, in other words, if you add a premise to some argument that is very dissimilar, it tends to reduce the strength of the argument. So we've talked about premise conclusion similarity, typicality effects, diversity effects, and monotonicity effects. More things means more evidence. This model cares a lot about overall similarity and overall coverage. So what's the problem with this model? The problem with this model is that it doesn't predict the inclusion fallacy. It predicts what you suggested, which is that people should make the right choice. People should choose the ostrich example in that inclusion fallacy. We should pay attention to category membership and coverage when making induction. But if people make different decisions, it suggests that they're considering things beyond just category membership. That's where Steve Sloman's feature coverage model comes into play. The feature coverage model adds two things to this diversity similarity coverage model. The feature coverage model suggests that most similarity is feature-driven. If similarity for natural kinds is primarily feature-driven, then induction should be primarily feature-driven, meaning that it doesn't really matter what category an object is in. What matters is that if premise and conclusion categories have a lot of things in common. Osherson calls that similarity. Sloman would just say they have a lot of features in common. And so the core idea is that inductive strength reflects the degree to which features of the premise categories are included or covered by features in the conclusion category, regardless of taxonomic structure. And so this allows the model to predict things about outliers and exceptional category members because it cares more about features and less about taxonomy. That's the one downside of Osherson's similarity coverage model, is that it relies heavily on that taxonomic hierarchical structure. Sloman's model does not. The easiest way to understand how the feature coverage model works is just to use the same example of horses, cows, dolphins, and mammals. And so you know about horses. You know what they do. They have fur, they breathe air. You know about dolphins. They're warm-blooded. They do technically have a very small amount of hair, but it's not really a feature that you associate with dolphins, right? They don't have fur. They have smooth skin. They have very trace amounts of hair. They don't live on land, so they don't have a lot of features in common. Cows also have a lot of features in common, but notice cows don't really add much. Cows and horses have essentially the same features. They don't cover as much of the space. By comparing or assuming that horses and dolphins are what you're drawing your inference from, you've added more features. You've added additional features, and it's much more likely that you can draw the conclusion to all mammals. So it makes it a stronger induction because you've just included more features. So that's the basic mechanism for Sloman's model. More features, stronger conclusions. Both of these models work pretty well for most of the effects we talked about, with the exception of the inclusion fallacy. Diversity, monotonicity, and so on. The key thing is this inclusion fallacy. People sometimes judge mammals and horses as stronger than mammals to animals, which suggests it's a fallacy. So we're making a direct conclusion. The feature set of mammals heavily overlaps with horses, but mammals covers animals less completely. It violates set inclusion, isn't predicted by the similarity coverage model, but it is predicted by Sloman's feature coverage model. So this is where the two models tend to diverge. Does this seem straightforward, or is this going to be a foggiest concept? I'm feeling kind of foggy myself. That's okay. I'll likely come back to this at the beginning of next week, because I do want to get to the last example, which has to do with causality. So I do want you to understand the difference between these, because I likely ask some questions. And the key thing to remember is this inclusion fallacy. It's not predicted by the similarity coverage model. It is predicted by the feature coverage model based on featural similarity. That tends to be the answer to one of the questions on the exam. There's usually a question about why people make mistakes in the inclusion fallacy. And the answer the correct answer in that case would depend on understanding this feature coverage. It's okay if it's a little foggy. I'm happy to review this. Yeah.
So under the feature coverage model, it'll say like people make the inclusion fallacy because robins have more features shared with all birds than
Yes.
penguins of all birds.
Exactly. So the feature coverage model predicts the fallacy, and which suggests it's a more robust model of how we actually think. Any model that predicts the errors is a model that predicts how humans think a little bit more accurately than a model that does not predict errors. Okay, let's move on. This is just saying the same thing. I think I had 3 slides that try to say exactly the same thing, and now I'm sort of questioning my decision to include 3 slides that say the same thing. I want to talk about causal links, and I want to talk about category coherence, and I think we've got enough time. Is everybody okay with that? I had 3 slides that made exactly the same point, so I just went through them. You still have them, but I just didn't want to. Is everybody all right with that? Okay. So we did this example in the QR code, and this is to suggest that sometimes the one thing that neither of these models works on. So Osherson's model works on understanding the taxonomy, understanding the hierarchical structure of the world. Sloman's model works on understanding features. Neither of them has anything to say about what causes those features. And so this suggests a challenge to both models, and that is whether or not you can recognize the causal links. Here's one that you did, and then I'll talk about an example we didn't do. In the first case, we've got example 1 and example 2. Cats have a parasite, field mice have it, and therefore all mammals have it, versus cats, tigers, and all mammals. The diversity effect, which is predictable by Osherson's model and Sloman's model, would suggest example 1 should be the stronger conclusion. But many people feel that example 2, cats, tigers, and mammals, is also a strong conclusion. And the reason is that it has to do with causality. This covers more of the category, but this also might highlight a causal link that doesn't have anything to do with category membership, doesn't have anything to do with features, but has to do with behavior. In other words, the knowledge might undermine the diversity effect. People might prefer the second argument because the first one, although being strong, suggests a causal link between the mouse and the cat, which is a hunting link. Cats catch it from the mice. And so it's really just a cat-mouse thing having to do with behavior. If this is a specific piece of knowledge about this causal link that you have that informs your reasoning, then you would be less likely to prefer that analogy. Does that seem clear? Might be clearer on the next one, which has to do with gazelles and lions. In this case, we just switched the two. Example number 1, gazelles have parasite X, therefore lions have parasite X. Lions have parasite X, gazelles have parasite X. Here we're not making a projection to all mammals. We're just saying if gazelles have it, do lions have it as well? Here the causal link is highlighted and makes a stronger induction because the first set of premise and conclusion highlights that causal link. Gazelles have it first, lions catch it from the gazelles because that's what they're hunting and eating. If gazelles have this parasite, lions catch it from them. Therefore, this is a stronger link, even though it's the same two premises. One premise is a gazelle, the other premise is a lion, but we reverse the order. The first one highlights the causal direction, therefore it's a stronger induction. So causality, in addition to category membership and feature overlap, also predicts inductions. The final one, here's another quick example, and then we'll come back to talking about some of these, has to do with the coherence of the category itself. Neither of these models predicts this very well. So go ahead and scan this, do a couple of examples, and then we'll talk about this one as our final example for the day. Probably thinking like, who thinks up these examples? This is what cognitive psychologists do. They think up examples like this. All right, let's see. How many responses do we have? Category coherence, 33 responses. I'll wait just a little bit. Oh, it's going to be so much more tiring next week, because we switch back to daylight saving time. Next week, it seems kind of early. What am I going to do with all that daylight? Shovel the driveway? I don't mind daylight saving time. I just mind doing it so early in March. Like, what am I supposed to do with evening daylight on March 9th? I mean, this makes no sense to me. Anyway, it's going to be worse if you feel like you're tired now. It's going to be awful next week
Next
because it's going to,
farming, no, good.
we'll get through it. I really appreciate you coming here today because I know how tiring it is on the week after the break. And I'll appreciate it next week too, even if you're late. All right, let's take a look at these examples and then we'll go through why they are the way they are. Presbyterian ministers preferring Coke to Pepsi. 80% of Presbyterian ministers drink Coke and not Pepsi. But 80% of waiters, for whatever reason, prefer Pepsi to Coke. All right, these are facts. We don't have to verify them. This is just based on if this is the state of the world. Chris is both a Presbyterian minister and a waiter. I don't know how you end up in both of those categories, but let's just assume that he's both of those categories. He had a stint as a waiter, and he also became a Presbyterian minister. Which of the two does he likely drink? And most of us chose Coca-Cola. So in other words, we think if he's going to have a beverage choice, it's going to be the beverage choice of his fellow Presbyterian ministers. Why is that? I mean, they're both equally likely. He's a member of both categories. They're both 80%. Why do you choose Coke in this case, which puts him in the Presbyterian minister camp and not the waiter camp?
I think because it's more niche, like there's
It's more niche. That's a great answer. It's definitely more niche. And by that, I assume you mean anybody can be a waiter, but it's a certain kind of person that wants to become a Presbyterian minister. First of all, you got to be a Presbyterian. And I mean, by definition, right? But like non-Presbyterians can be waiters. Anybody can be a waiter, but only Presbyterians can be a Presbyterian minister.
I find like being minister would be more close to who the person is.
Ah, good answer. Close to who the person is, right? Because minister is like, that's a real, it's niche, but it's close to what the person believes. This has something to do with the core of the person, whereas waiter, I mean, lots of people might really heavily identify with their job serving, but many other times it's a job that you do while you're going to do something else later. And so that's why we would say that. So science fiction people who love science fiction prefer vacationing in Bermuda to the Bahamas. But carpet manufacturers prefer vacationing to the Bahamas in Bermuda. I'm already getting confused. Timothy, carpet manufacturer, science fiction reader, what is he like? And here we give him Bermuda, which means that he's much more like the science fiction addicts. And I think the answer is probably the same. That you would choose to put him in something that's a little bit more passionate. Now, maybe science fiction aficionados is not quite as niche as Presbyterian minister, but it aligns with what you said, which is it's something that you really care about. Carpet manufacturing you might care about, but maybe not in the same way. If you work at a carpet factory, maybe it's your job, but you don't hang out with fellow carpet manufacturers, but maybe you like to hang out with fellow science fiction nerds. And so you go to the same vacation spots that fellow science fiction nerds go to. So it has something to do with what that category is. And I think were there just the two? I think they were just the two. And this has to do with the coherence of the category. So if we make inductions based on categories, which we agree we've done, philosophers suggest we should do this, our own research that we've talked about in this class suggests that we do it, and those categories are formed around features. We've got two models that seem to predict that, but neither of them have anything to say about the coherence of the category. In other words, how tightly structured is that category? How meaningful is that category? Birds are just birds, right? I mean, robins and penguins are equally coherent categories, so it really doesn't matter. But it does matter for lots of categories like waiter, Presbyterian minister, police officer in this case. Inductions are made from concepts and categories on the basis of similarity, but coherence plays a role. Let's say police officer, that's another category. It's a pretty coherent category. A certain kind of person probably wants to become a police officer. Maybe being a police officer identifies you with other police officers, and maybe you have behaviors, preferences, and so on that are similar to your fellow law enforcement agents. We expect there to be a high degree of similarity among people who join the police. Might expect them to share features, traits, and behaviors. Upon hearing that someone is a police officer, we might feel confident in knowing how they might act and behave. That's the reasoning or the rationale that we used in choosing to assign the beverage preference to a person who was a member of multiple categories. We chose the one that seemed to be more coherent, Presbyterian minister. And if we had the same thing with police officer and waiter, we might assume that to be the case. Restaurant waiter, which was the other category we were considering, seems less coherent. There's probably more diversity in this category and more reasons why you might choose to be a server in a restaurant. One is sort of closer to your core. The other one might just be something you do. This was studied in a couple of different experiments, but I'll talk about the one which you participated in, some of the examples in, Patalano, Chin Parker, and Brian Ross. So they asked participants in their study to consider the social and occupational categories that were higher or lower in coherence. They described coherence in a number of ways, but they measured it with something called category entitativity, which is a tough word for me to say on any day, particularly tough today. Entitativity kind of gets close to what you said over here, which is it has something to do with the core of the person who is in that category. Police officer, Presbyterian minister have high entitativity. There's something, an entity about that category. There's some sort of essence in that category. Or as you said, it's kind of niche, right? You really want to be a minister. Anybody can be a waiter. Does everybody get that idea? So some of these categories have high entitativity, meaning that not only are they tight and close, we also expect them to be tight and close, and there to be some kind of cause, some reason why they're tight and close. In this case, something that has to do with your core beliefs. Soldier, feminist supporter, which we saw on the Tversky and Kahneman example. Minister, highly coherent. Matchbook collector, not very coherent. Anybody can collect matchbooks. I don't know why you would. County clerk, it says country clerk, but I mean county clerk. Limousine driver, low in coherence. Anybody can drive, can be a checker cab driver, right? Maybe it's not a very coherent category relative to minister. That doesn't mean it has no coherence. It just means that it's relatively less. And so, as we saw, feminist supporters, they carried out a category, an induction task in which people were asked to make predictions about people who were members of more than one category. And we would see things like feminist supporters, Coke to Pepsi, waiters, Pepsi to Coke, Chris, feminist supporter, and a waiter, what beverage? And that's the one that we did with minister instead of feminist supporter, but the same idea, high coherence and low coherence. And what they found is that participants, just like you, chose to reason from the high coherence category. People in their experiments preferred to make inductions on the more coherent category. Chris is likely to prefer Coca-Cola. In this case, people view feminist supporter as the more coherent category. They prefer to base their inductions on that category. I asked last year when I was doing this lecture, this is from last year's investigation. I don't know if ChatGPT has gotten any better, but I asked last year's version of ChatGPT, which I don't remember what version that was, to carry out exactly the same problem. I said, hi, premise, 80% of feminist supporters prefer Coke, 80% of waiters prefer Pepsi. Chris is a feminist supporter and a waiter. What beverage? ChatGPT says this problem presents a logical paradox because Chris belongs to two groups with conflicting preferences. Feminist supporters like Coke, waiters like Pepsi. Chris is both groups. Since the premises do not specify how to weigh these competing preferences, conclusion is indeterminate. Chris's preference is ambiguous because we lack additional information about how their dual identity affects their choice. Would you like me to reframe this? I did not. I would like you to draw a conclusion. Don't reframe this, just choose which one based on the information given. I understand is it a paradox. Could you make a decision based on the coherence of each category? So let's analyze. Feminist supporters, 80% prefer Coke. Probability of Chris performing Coke, 80%. 80% prefer Pepsi, 8.8. So it hasn't really solved anything. Chris belongs to both groups, but we don't know how much influence. However, if we assume both identities hold equal weight, yet we encounter a contradiction. So far, ChatGPT is stumped. It cannot reason its way through this. So it tries to resolve the conflict. Since each preference is 80, we might assume that Chris is equally influenced. This would lead to the ambiguous, you've said this 3 times now. However, if we consider the coherence, feminist support is likely based on ideological or lifestyle preferences. Waiters makes his choice based on workplace exposure and occupational preference. If ideological feminist is a stronger personal identity, then Chris is more likely to side with the feminist supporters. Thus, the best possible conclusion is that Chris is more likely to prefer Coke. So I had to nudge the generative AI, but it solved the problem. And I said, thank you, that is a good answer. It's also the conclusion the majority of humans endorse, and for the same reason. Good job reasoning like a human. Thank you. I appreciate the challenge and the validation. If you have more paradoxes, I'd love to tackle them. So induction is natural. As we said before, we have lots of bad information available to us at any given time. We've got good and bad information. We have to choose. Conspiracies, we talked about conspiracies providing a coherent worldview. So if induction is natural based on concepts, categories, similarity, and coherence, if it seems to provide too easy of an answer, it might be worth rethinking. Okay, that's all I've got for today. Next week, we have a quiz we're going to talk about deductive logic and causal reasoning, and then we're going to have a quiz based on units 6 and 7. I do have a slide that has the QR code for foggiest concepts, and I kind of feel myself as if some of the categorical reasoning felt a little foggy to me when I was explaining it. But if there are other things you'd like me to go through again at the beginning of next class, just let me know what you'd like to see. All right, see you next week. At the beginning of summer daylight saving time. Yeah.
Just